Today we're going to talk about how to differentiate products of functions and quotients of functions, and we're going to start with the product of two functions. So f of x, g of x prime is, using our definition, the limit h goes to 0 of f of x plus h, g of x plus h, minus f of x, g of x over h. Now it's not immediately apparent what to do at this point, but there's a trick, and the trick is we add f of x times g of x plus h minus f of x g of x plus h to the numerator. Now this term right here is 0, so it doesn't change the answer, but it allows us to regroup things, this term and this term together, and this term and this term together. And when we do that, what we see is that this term has a g of x plus h, which will factor right out, and this term has an f of x, which will factor right out. When we do that, we end up with the lim as h goes to 0 of g of x plus h times this limit, which if you look at it is f prime. And this limit is the limit as h goes to 0 of f of x. And if you look at this, this is g prime. Now, h is not involved, so the limit h goes to 0 of f of x is f of x. The limit as h goes to 0 of g of x plus h is just g of x. So we get g of x times f prime plus f of x times g prime. And I'm going to rewrite that now because these things commute. F prime of x times g of x plus f of x g prime of x. That's the derivative of f of x times g of x, and that's the product rule. The derivative of f of x times g of x is the derivative of f times g plus f times the derivative of g. So let's look at an example. The polynomial x squared plus 3x plus 2 times the polynomial x cubed plus x minus 1. And the product rule says it's the derivative of the first times the second plus the first times the derivative of the second. And what's left to do is to calculate those derivatives. The derivative of x squared plus 3x plus 2 is 2x plus 3. And the derivative of x cubed plus x minus 1 is 3x squared plus 1, and that's the answer. Now let's talk about the quotient of functions. Now here I'm not going to derive anything. What I'm going to tell you, however, is if we started off with that same definition and did some rearranging, the same sort of trick would lead us to this, and this is the quotient rule. Now, in the product rule, it didn't matter which of them we thought of as f and which of them we thought of as g. Here it does. F is the numerator, g is the denominator. So it's denominator times derivative of numerator minus numerator times derivative of denominator over denominator squared. So for example, the derivative of x squared plus 1 over 3x minus 4 is given by the quotient rule. So we get denominator 3x minus 4 times derivative of numerator, which is x squared plus 1, minus the numerator x squared plus 1 times the derivative of the denominator 3x minus 4 over the denominator squared. Now when we do this calculation, the derivative of x squared plus 1 is 2x, the derivative of 3x minus 4 is 3, and this expression is the derivative of the quotient. Now we can simplify this by multiplying out the terms in the top and then subtracting, and we end up with the following expression, which is equivalent to our answer up here. So this is the answer. This is just a simplified form of it. We know what the derivative of x to the n is when n is a positive integer. What is it when it's a negative integer? So we're going to write x to the minus n here where n is a positive integer. Now we know by laws of exponents that's 1 over x to the n. So when we're taking the derivative, we can use the quotient rule. And we get denominator times the derivative of the numerator, and the derivative of 1 is 0, minus the numerator times the derivative of the denominator, and now we can use the power rule, which is nx to the n minus 1 over x to the n squared. Now when we simplify this, the only thing we get in the top is the minus nx to the n minus 1. This is x to the 2n. And now when we slide the x to the n minus 1 into the denominator, we're subtracting n minus 1 from 2n, which gets us n plus 1 as this exponent. There's a minus n in the numerator. And that's n times x to the minus n minus 1, which you'll notice is exponent goes out in front, and the exponent in the derivative drops by 1. That's the power rule. It's just true for negative exponents as well. We actually also calculated earlier the derivative of the square root of x, which I'm writing now as x to the 1/2. And what we got as an answer was 1/2 x to the minus 1/2. And if you look at that, the power rule works here too. This is not an accident. The power rule works for all real numbers. So no matter what your exponent is in x to the n, the derivative of x to the n is nx to the n minus 1. As an example, let's take the derivative of 1 over the square root of x cubed, which we can write as 1 over x to the 3/2, and then as x to the minus 3/2. Now the power rule tells us the derivative is minus 3/2, the exponent, times x to the minus 3/2 minus 1, which is minus 3/2 x to the minus 5/2. Suppose the only things we know about f are the values of f and its derivative at 2, and suppose that g is defined as x cubed f of x. We cannot find the general derivative, but we can find the derivative of g at 2, and we're going to use the product rule. So g prime is the derivative of x cubed f of x, and according to the product rule, that's the derivative of x cubed times f of x plus x cubed times the derivative of f of x. And the derivative of x cubed is 3x squared, and the derivative of f is f prime. And now we're going to just use the information that we've got. G prime of 2 is going to be 3x squared, which is 3/2 squared, times f of 2, plus x cubed, which is 2 cubed, f prime of 2. 3 times 2 squared is 12. F of 2 is minus 1, and 2 cubed is 8. F prime of 2 is 3, and we get 12 times minus 1 plus 8 times 3, which is minus 12 plus 24, or 12. This will be a brief trigonometry review. We start with the unit circle, x squared plus y squared equals 1. We look at an angle theta. One of the sides is the positive x-axis, and we look at where the other side intersects our circle, x squared plus y squared equals 1. The x-coordinate is the cosine of theta. The y-coordinate is the sine of theta. And since we're on x squared plus y squared equals 1, that reads cosine theta squared plus sine theta squared equals 1. Now notationally, we write cosine theta quantity squared as cosine squared theta. So another way to write this is cosine squared theta plus sine squared theta equals 1. Now, how does this correspond to the triangle definition that you've seen before? If you look at this triangle and move it down here, the base is the x-coordinate, cosine theta. The height is the y-coordinate, sine theta. And now if we look at a triangle with sides A, B, and C with that same angle, we see they're similar triangles. And what we can see is sine theta over 1 is the same as A over C, and cosine theta 1 is the same as B over C. So the sine of theta is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse. Now, how do we measure angles? On our unit circle, the radian measure of the angle theta will be the length of this arc, the arc between the two sides of the angle. And the circumference of our unit circle is 2 pi r, and the radius is 1, so that's 2 pi. So there are 2 pi radians in a circle, which is 360 degrees. This allows us to convert between the two measures. So you take 360 and you divide through, and you get 1 degree is 2 pi over 360, or pi over 180 radians. You do the reverse to convert from radians to degrees. 1 radian we divide through by 2 pi is 360 over 2 pi, or 180 over pi degrees. So for example, 60 degrees will be 60 times the pi over 180 radians, pi over 3 radians. And pi over 2 radians is going to be pi over 2 times 180 over pi, 90 degrees. Now let's calculate the sine and cosine of some special angles. So we look at pi over 4, which is half of pi over 2, which you remember was 90 degrees. So this is 45 degrees. This is right along the line y equals x. So sine theta cosine theta sits on x squared plus y squared equals 1. So we have the identity cosine squared pi over 4 plus sine squared pi over 4 is 1. But we're in y equals x, so cosine equals sine. This is then cosine squared plus cosine squared equals 1, or 2 cosine squared equals 1. We divide through by 2. Cosine squared is 1/2, and that means the cosine is plus or minus 1 over root 2. However, pi over 4 is in the first quadrant. These are positive numbers up here. So the cosine of pi over 4 is greater than 0, which means the cosine of pi over 4 is 1 over root 2. And because we're on y equals x, that means the sine of pi over 4 equals the cosine of pi over 4 equals 1 over root 2. Now let's look at a couple of these other points. 1, 0 is an angle of 0. First coordinate is 1, second coordinate is 0. So the cosine of 0 is 1, and the sine of 0 is 0. If we look up here, this is 90 degrees, or pi over 2. Cosine 0, sine 1. So the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. Let's look at a couple of other angles. Now you probably remember from high school the 30, 60, 90 triangle with sides 1, root 3, and 2. The radian measure of 30 degrees is pi over 6. So we can read off the sine and the cosine from here. We can see that the cosine is going to be adjacent over hypotenuse, which is the square root of 3 over 2. And we can see that the sine is going to be opposite over hypotenuse, which is going to be 1 over 2. And that's absolutely reversed for pi over 3 because we just switched the roles of the angles. Now, how do we find sines and cosines in quadrants other than the first quadrant? Well, we use some symmetries. So you can see here theta, we get to the point AB. If we were to do minus theta, we would be at the point minus A minus B. And if we put the theta over here, we can see this angle pi minus theta is going to be in the second quadrant and is going to have coordinates minus AB. So for example, if this angle is pi over 3 and the cosine is 1/2, which is the first coordinate, when we go down here, we're going to have the same first coordinate. So the cosine of minus pi over 3 is also going to be 1/2. When we go over here, this is going to be pi over 3. Pi minus pi over 3 is 2 pi over 3. So we're going to conclude that the cosine of 2 pi over 3 is minus 1/2. Now we should mention that there are some other trig functions. The tangent is the sine over the cosine. The cotangent is just the opposite, the cosine over the sine. The secant is 1 over the cosine, and the cosecant is 1 over the sine. So if you know sine and cosine, you know all of the trig functions. To illustrate all of this, let's do one final example. Suppose that we know that the sine is 2/3, and our angle is between pi over 2 and pi, which is second quadrant. We want to find the cosine and the tangent. We start with the relationship cosine squared plus sine squared equals 1. We know that sine is 2/3, so we substitute for the sine, and we get cosine squared plus 2/3 squared is 1. 2/3 squared is 4/9. When you subtract 4/9, you get that the cosine squared is 5/9, and thus the cosine is plus or minus the square root of 5/9, which is plus or minus the square root of 5/3. Now, we're in the second quadrant. We look up here, first coordinate, which is cosine, is negative, so that means that our cosine is minus the square root of 5/3, and the tangent is just going to be the sine over the cosine, which is our 2/3 divided by minus the square root of 5/3, which is minus 2 over the square root of 5.